If you can show me how the actually by step, how to first configure the things, such will be better.
I'm just starting Zoom, the YouTube recording. So once it starts, okay. So as I mentioned, Andrew is going to be a bit late. He's going to come maybe in 30 minutes. And will demonstrate to us some DBH calculations with MMCTP, comparison with the treatment planning, and so on. So meanwhile, I can demonstrate how you can actually install MMCTP or configuring MMCTP. Okay. Okay. So this is actually my Raspberry Pi. Okay, I have everything, not a virtual machine, but on my Raspberries. I have a directory. I have actually configured EGS, installed it, and it's actually not under my username, but a different username, MMCTP, I called it. So if I switch to that, okay, okay, so let me close this. Okay, so I have my EGS directory. If I do ls/la, you find the EGS directory. All of you have this if you have installed EGS. And then inside it, I have a Beam directory. So I remove the other user codes. I don't need them. I need only a Beam and those XYZ. But if you have the those RZ, all of the other codes, like as if you installed EGS fully, that is still fine. No problem with that. So the Beam is there, and we have went through actually making the Beam and making an input file those XYZ to use Beam as a library or to use a source as a face-based file. We have went through all of that. So I just wanted to show you there is nothing really special on my Beam, on my EGS side. The only thing I have, maybe different than all of you, is I have this directory. I call it face-based. This directory has the sources for my Beam. With Variant Linux, remember they don't give you anything above the JAWS, the geometry. So they give you a face-based file that represents the particles just coming above the JAWS. And then they give the geometry for the JAWS, the MLCs, and if you're using electrons to be for applicators and so on. So I'm using the face-based file as a source for the Beam simulation, Beam model. So just to show you, we can, let me go back and I'll go back, switch back to my user, Beam. Okay. So I'm going to open the accelerator. So I have the TrueBeam accelerator with an input file. This is an example input file and the PEGS data file. So all what I'm talking about is pre-MMCTP, okay, just so that you understand the configuration. And for my variant machines, I just have 3 component modules. Those, the dynamic JAWS, dynamic MLC, and slabs. That's the exit window, and probably air and my input file is a face-based file. Okay, and if I select, so that is 21. So you'll find it's actually pointing to that directory, or it's not in my, but it's pointing to a face-based directory file. That's the whole point. You can keep it locally in the Beam directory. That's up to you. Okay. So I have an example of an input file that works. I've done, uh, well, let's say Monte Carlo commissioned the machine. Okay. So everything is working, or the Beam. So now we go back and see what we need to do with MMCTP. So let me open MMCTP. Okay, so I'm going to run it actually from the code itself. So we'll just run it. It takes time, a bit of time to compile, but now I think it's going to start. Okay, so it's fine. So probably with the first time you run MMCTP, you will not have patience. You will not have these things. You will have something black, but you will have this window. So the first thing we need to do is to configure it, and that's through we need to first configure remote shells. This is what I usually do. I will go and configure remote shells. This is basically where do I have my EGS directory, or computer that is going to perform the calculation, EGS Monte Carlo calculation. So this is called shells. So now I have, as you see, I have already one shell configured. Suppose I'm going to delete it. Okay, so you will get a new shell. Then you just start typing the name. My shell, I call it Raspberry uh, 01, okay, because that's the machine I'm submitting to it. And then I will put the IP. That's the IP of my machine. Okay, it's a Linux machine. If you're running this on a Linux, you can put this IP. So this is always your local machine, 127.0.0.1. That is your local machine. So if, for example, like in your case, Bilal, you said you installed the Linux version on your Linux machine, then you can put
So both can
this
reside in
IP.
the same machine. Both
What's
can,
that?
MMCTP as well as EGS can reside in the same machine.
Yes, the problem, this is what Andrew confirmed last time, is that you need to, any submission has to go through SSH, FTP, okay? So we have to deal with IPs. But what you can do is you can just type 127.0.0.1. This always
Local host.
points
Yeah.
to your local machine or local host, okay? So this, in my case, my machine is dot 8.1, dot 11. Okay. Now the user, I I have planned to actually do the simulations under a user on my Raspberry Pi. The user is called MMCTP. I've added a user and I want to use that user. Okay, it's up to you. You want to have your own, like I could, for example, type Wabdel and put the password for my account. Okay, this part is important. As I mentioned last time, MMCTP, and this is why I actually make a different user. MMCTP needs to know, for example, when an execute when the prompt is available to execute commands. So this is the line feed prompt. So basically, MMCTP, or when this application runs, it's going to look for a dollar sign. And when the dollar sign is there, then it understands, okay, now I can execute a command. Of course, having a dollar sign, this is not good only, because you know you can have a dollar sign from like in a file name or anything. So what they recommend is that the line feed, you call it the user MMCTP dollar sign, sign, okay? But we need to make sure that we actually we change the prompt for MMCTP, the user. So now, for example, you see my user. This is now I've opened the shell. The prompt is actually the MMCTP dollar sign. So when I enter,
Dash RC.
that's always going to be there. Okay. If I change this, and how to do this, that is very simple. So we go to the
Dash
bash
RC. Okay. Yeah.
RC, and we need to add. Uh, we need to add. Well, it's this. Okay. Let's see if I can. I don't know how to. Yeah. Okay. So it's this. Okay. This is of course the configuration of the AGS itself. That's fine. This is something you don't have to worry about. It's an aliases that I use, but we need, this is basically defining the prompt, how the prompt is going to look like. Okay. So for example, if I remove this dollar sign, then you see the prompt is actually the word MMCTP. If I change it, so slash y slash u is the username. I can make it anything. I can say hello, for example. That's fine. So now the prompt is going to be the word hello. Got it?
Yes, yes, I get it. Yeah.
Okay. So we'll just so you know you can select anything you want. Okay, but because MMCTP needs to actually find this in the text and say, oh, okay, now I can execute a command. When I see this word MMCTP, you can make it something longer. You know, that's better even.
Mm.
Okay, but something that's not common. That's for example, is not the machine name, because usually we will always have, you know, the machine name actually you know, in the prompt. So, so this is what they recommend, and that's why I have put it here: MMCTP dollar sign. The shell is bash. Okay, I'm using a bash shell, and once I have this, then we can test the connection. So let's test it. Oh yeah, I did not put the password. Oh yeah, I have to change it. So the user is MMCTP, and then I need to put the password for that user. Okay, so now you see the connection is okay. The other thing is important is here. This is just a test. So I usually use the secure FTP. So select this and connect test, connection test. You should get the okay. When I use the FTP, because I did not install an FTP server, I installed a secure FTP server. So that's why it gives me fail. So now for this shell, I'm using secure FTP. So this to connection test, that's fine. So far, so good.
Suppose we have installed the FTP, then what should happen? What should be in the test prompt?
Where?
The
Here?
test prompt, yes, yes, yes. It is FTP
Uh,
only.
Yeah, I think maybe FTP. I'm not sure because usually I use the secure FTP, so I don't worry about this.
Okay.
And
So we have to install separately this secure FTP.
yeah, it's there is one that I use. It's called VS Very Secure FTP
VSFTP,
Daemon.
VSFTPDS.
Yeah, that's you need to change one line in the configuration, so it will allow users to. I think did I describe it in
No,
the
it is there in
yeah,
the actually the AGS cluster one you installed that you
yes,
said.
so it's there. Okay, then then the next thing is, okay, what's the queue on that system? Okay, or the batch, the queuing system. So if you don't have Slurm, you can use 80. It will submit and it will use 80. So it will submit things using the exb command, and I mean, it will launch using the default 80, uh, what they call it, parallel processing system or package. But in my case, I'm using Slurm, so I will select Slurm. And with Slurm, there are many queues. I only have one queue, so I could just leave this blank, or I could actually type in the queue name. Okay, a number of queues here. I'm gonna put one. Okay, and the name. Maximum number of running jobs. I have 50. Okay, I could put 100 because when you have a queuing system, this is what I like about Slurm is then uh, you submit and you're submitting to Slurm, and Slurm will actually not launch the execution of the commands until it has an available slot. So I can launch, as many jobs. It will just be queued there. With 80, you cannot do that. It will actually launch everything. So you end up by the CPU, instead of having 100, it will be shared among all the jobs that you're running, and it just drops. So this is important here. Where is the EGS folder located in that shell? So in my case, it's under Home, MMCTP, EGS Home. Okay, so that's where the EGS folder is in my cluster. Depending on how you install EGS, you might have something different. So once this is done, then that is the configuration of the shell. Okay, so far so good.
It will automatically save the information there.
Yeah, it will, whenever you change something, it automatically saves it. So don't worry about that. Okay. So the next step, okay, Ryan artifact. Okay, I'm gonna run it from the compiled version, not okay. It did not take a long time to compile this time. Then the next thing you'll do is the configuration. We need to configure the B model. CTO model, usually it will have one by default, the H2O RAM. That is something, not important now, but the B model, that is important. So we'll go and configure B models. So I have, for example, you will start selecting a B model, photon, call it whatever you want. I call it True Beam Rose because that is uh, the machine that I'm going to get from. And by the way, when you import a DICOM, it will automatically, from the DICOM, it will automatically create for you the machine and the energy from the DICOM file. So once you import the DICOM, then you will find a Linux configured. Like now I have an energy 2.5, and definitely that's not what I have. We don't treat with this, but because one of the files, or actually the DICOM contained imaging files, set of fields, and the setup field is the energy was defined 2.5 MV. That's why when I imported the plan, it created for me that energy. I can delete it. I just left it, but I can delete it. So if you don't know, for example, what is the Linux name or the energy, easiest thing is you import DICOM RT from your planning system. Then it should capture the machine name, the energy, and so on. And then you can come here. So when you open it, you will find, okay, now I have a machine. I can define actually what that machine is. Varian, Electa, Cyberknife, Siemens, chemotherapy, or other. So Varian,
So
this is my
data should
machine.
contain the RT structure. Everything should be imported here. Everything.
Yeah, but you don't, it's not from here. The import is from a different location.
Okay.
I'm going to show you how to import, but I'm just showing you how to configure a machine, a beam.
Okay.
So now we have a machine, a beam, a photon. Okay, we just define, is it variant? We select the machine type. Then MLC settings. When you import, this will be populated automatically. So you also don't need to worry about this. Okay, because the MLCs will probably be embedded in the, but make sure you import a file that has MLCs in it, a DICOM RT, not just an open field, but at least if you can make it, you import a 10 by 10 field, but add to it MLCs. So then it will capture the MLCs and put them for you. Otherwise, you have to put these values manually. So in my case, the number of binary leaves, the number of leaf pairs are 60 for the Millennium MLC. And air gap, I put this value. Maybe this is too small, I'm not sure. But here, this is, you need to put where is that, or the boundaries for the leaves. So for example, leaf number 1, that is at -20. Leaf 2, -19, and so on, okay? The leaf direction, for the variant, they are parallel to the X jaws, okay? This part,
Can we edit this value also? These values can be
you
edited.
can, we can edit this, okay? You can do whatever you want. So I can put, you know, so for example, for a high definition MLCs, this is going to be different. The values are going to be different. So my suggestion is just import a file. Instead of trying to figure out where are these values and so on, try to import a file from a DICOM RT file into MMCTP. I think it should populate all of this stuff for you automatically. So you need to select what machine is there, and then the MLC setting. This, I think, will be populated automatically. And yeah, I'm not sure about the sinogram. This thing is, you know, I don't know if this is for a different, I mean, when Andrew is here, we can ask her about these things, okay?
Sinogram is there in tomotherapy, I think.
So this is, so tomotherapy, they have sinograms
Yes.
for the MLCs.
Yes.
Okay. This is the MLC source to device distance. Okay, that is from you know, variant the model, the geometry. So the MLCs are 48.175. This value I've entered manually. Okay. Then the accessory settings, if you want to add, for example, physical wedges, or if you want to add a dynamic wedge. Okay. Dynamic wedge, we need this STT file. So you just, it is actually, I put it somewhere, it's in a direct, I have a folder that has these settings for MMCTP. Let's look at it. It's, and yeah, it should be, for Mac, it should be under library, so on. But maybe for other systems, it's going to be a different location. You can ignore it if you don't want to use dynamic wedges. at the beginning, you can ignore it. We can always add things, physical wedges. If you want to add physical wedges with their ventilation, you can do this. Okay. I did not add any of these because we don't actually use physical wedges in our clinic, and dynamic wedges also. I mean, most of the time we rarely use them actually. This part is important. So here, when you start doing MMCTP and calculation of fields, uh, you can do it. Obviously, you will need to first generate a phase space file from the beam, and we're telling the system, look, probably we want to have a particle density of about 500,000 per centimeter squared, I think. So the system initially, it will submit a calculation to see how many particles it needs to actually run in order to get roughly this particle density in the phase space file that you are going to use directly on those XYZ. Frankly, I don't do it this way. I use beam libraries, but some people would like to actually generate phase space files. So this is a value. This value, you can change it. You can say, look, I don't want this density. Probably 10,000 is going to be fine. I'm happy with that. It's up to you, okay? But it's a value that they have. This second line is important. This is an example of an input file for the beam. So I've actually grabbed an input file that works with TrueBeam, my beam model, and I put it in a location, and then I'm telling the system, look, use this as an input file. It doesn't, mine is for a 10 by 10 field. Okay, so this is the input file. It's telling the system, I mean, there are stuff that are standard, it's not going to change, but definitely MMCTP is going to change the component mode. It's going to change this dynamic jaws, the MLCs, and this probably is not going to change it because that is always going to be fixed. I've also fixed here some of the physics parameters that I personally like to like have atomic relaxation on, Compton on. So in the template file, I put all of this stuff here. Okay.
Dr. Rahman, if we score the phase space at some, like this phase space was scored at 70 centimeter. If we change it at 80 centimeter, then is MMCTP is capable to calculate the dose at different distances, like
No, I
different
think
SSD?
MMCTP will always require you to calculate the phase space file to 70. So in your input file,
Okay.
it's to 70 centimeters because its assumption is we're going to actually add a patient, right? So the phase space file, and most of the treatments are SAD. So we want to be the phase space file to be away from the patient's surface. So it's about 30 centimeters away from isocenter.
Is it
So
possible
the
to
patient thickness has to be 60 centimeters in order for you start having problem. Okay.
Okay. Is it possible to calculate the doses for SSD setup? Like in Cobalt 60, we want to calculate the dose in a
You can. I'm struggling with something, but we can. I'm sure we can. It's this physics patient that I'm struggling to create, but we can always generate this, and I can show you. Actually, so
Okay.
Andrew probably is going to come soon, but so here, this is my shell, Raspberry. You will find this thing blank. We need to actually enter what is the directory for my beam. So the directory is to beam. Okay, so that is my directory in the cluster, because the Linux directory is called, remember in the shell we created only or we told the system where is the Monte Carlo directory, EGS directory, and under that, this is going to be the beam folder name. So that's all what I need. This thing is for end use. I'm also struggling with configuring this part because I cannot make, but basically with Monte Carlo, we define what is the dose per particle equivalent to in terms of end use. So ideally what we should do is we should run a simulation. Let's say for a 10 by 10 field, SSD setup, and run a simulation for dose, and then see what is the dose at one, let's say at Dmax 1.5 central axis. In our case, our beams are defined so that the dose to that point is 1 centigrade per monitor unit. So I look at what is the dose recorded from Monte Carlo. It's, let's say, 3.2 10 to the power minus 14 grays per particle. I will take that. That is equivalent then to 1 centigrade per monitor unit. Then if we change the jaws, then with the dose to the dose is going to be different to Dmax. And using that conversion, I'm going to be able to actually calculate monitor units or so on. Okay. So we're done. Here I have two because I think there are two shells. So let me clear this shell again. Yeah, this one I'm going to delete. Okay, so I have one laser instead. So this patient, I'm struggling with this patient, but let me show you what, I mean, this is what I want to do actually. So the patient, when I created the patient, uh, I changed actually. You see this, I want you to imagine, I have a patient, the patient is, or a phantom, the phantom has a thickness in this direction of 40 centimeters. So the ISO 000 is here, then the surface is at minus 20, and this the other side is at 20 centimeters. So I've created a beam, I selected my energy, and I'm telling the system, look, the isocenter is going to be at minus 20. So the if the isocenter is at 000, then it's going to be at the middle of this phantom. But 0 minus 20, that means the center is actually at the top of the surface. The problem I'm facing with this setup is when I look at the phantom, okay, you see everything is air. I'm not getting water. I want this phantom, whatever is here, I want it to be water, and I cannot do that. I have a problem. Uh, so Andrew might help me here. Okay, now the material is air. I see something different. So the material is air is in this is one. This one could be used, but so I struggled a lot really to create this fan with this part. Let me delete this again. Okay, I'm going to delete the patient. So I show you, for example, how we can do this physics part. Import, by the way, it's here. So if you go to File, Import, RT Patients, there should be a folder where you're actually putting your DICOM files. You put your folder, your DICOM files there, and it will automatically read that folder. So in this case, my folder is actually under its MMCTP DICOM. So if I show you in my documents, I have a folder called MMCTP, and I have all of these. So folder for beam, I have specific folder for beam configuration, beam NRC. DICOM, I have a folder for DICOM. These are the DICOM files. Or I just export them from Eclipse and put them in this folder. And to set up where the system can find these folders or to define them is here. So we go to configuration, the system admin settings, okay, the folder locations. So if you look at what I've done, let's say for the DICOM, this is the DICOM folder. So I told the system, look, the DICOM, any DICOM file, you're probably going to find it in that folder. So when I, here, when we start, okay, import. Okay, this is the, here I can actually, instead of getting a DICOM, I can create actually a patient or a phantom. And that's what physics is supposed to do. So when I hit on physics, I can physics and I can give it a name. So let's do, okay, I want to distinguish it from the other one. Okay, image size. This is the number of, so in the X and Y direction, that's axial cut. I want 512 by 512. We can reduce this. It doesn't need to be that number of voxels. And this is the number of slices. Okay, so I have 40. And here, so I want the slice to be 1 centimeter. I can increase this. It's not a problem. And this is the coordinate of the first Z, X, and Y. So imagine a cube. So the first coordinate, minus 20, minus 20, minus 20. So that's the corner of the cube. And when I create the patient, just give me a minute. Okay. So if I open again, I should find that patient here, physics. Open. And it should automatically create for me the phantom. So creation of phantom is just, okay, I have these voxels. It's now going to put or define the medium for the voxels and their densities. Okay. So here it is. We'll start with putting a beam. I can click on this side, add a plan, and then select on the plan. Then I can add a beam here and photon. I have my machine and energy. Okay, that's fine. Energy. This is your geometry. It's a 10 by 10. If I have MLCs that I want to import MLC file or modify, we can do this here. But since I want something very, just a static field, I'm going to keep it as is. And this, I'm going to change this to be minus 20. Okay. If I want 100 SSD, this MMCTP does not, because first I don't have a contour, so you will find this to be 0 because it does not know where is actually the surface of the body. But I also found that it does not even do that with CT images, at least in my version. I don't know if Andrew has something that does this or not. But it's not important for me to actually define what is the SSD. The important thing is the coordinate of the isocenter. So imagine your patient, the patient, and that patient, what we've defined is at the center of the patient, we have the coordinate 0, 0, 0. So I'm putting the center 20 centimeters anteriorly. That will make this field 100 SSD. So when I look at the phantom, this is what I don't like about it. You look here, this is the material, it's air. I want everything to be changed to water. Okay? One way to, I've tried several things. So I went here to generate a new X phantom, but it still does not work, at least in my Mac version. So since I don't have a contour, okay, material outside contour, that's not there. But I should be able to do manual setting. So manually assign voxels. So remember the voxels, we have one, let's put the material. Okay, and okay, I cannot change these values. That is a problem because I don't have, it's not 133, it should be 512. And this also from 1 to 512, and this will be from 1 up to 40. So maybe this is the source of, yeah, I cannot change these values. So there is a problem. I cannot do this actually with the current version. So this is something we can tell Andrew about, because I should be able to actually define these values. So anyway, uh, maybe we can do something else. Let's see if I can change this to water. Um, so what it's trying to do is to assign voxels, and now writing the phantom. And we can see if everything is done properly or not. I think it should give me a message now that it's finished. Okay, so this is the problem I've always been facing. The density is 0. So when you do a calculation, there is no dose going to be recorded. So there is a problem I'm facing in this phantom.
Do we need to change the CT ramp values actually in the initial configuration
No, but
because of
it's
this?
not a CT ramp. It's, I'm making a manual phantom.
No,
Okay,
maybe actually
so
we have to give some values for this. It's not able to assign its values.
the CT ramp, well, first, we don't have CT values. Okay, for this patient, we just define the geometry, but there are no CT values, CT numbers, Hansfield units, right? So even if you want to use the CT ramp, I don't believe it's going to work because there is no image. That's the problem. Here, I should be able, to manually assign boxes, 1 up to 33. Well, let's try this, okay? But it's not doing it properly. Let's try it. At least I should get some boxes to one, different water, but I'm not getting that. So this is a problem I'm facing for here. If this is done, then we can actually use MMCTP when we are commissioning actually our green accelerators, or to test, for example, okay, do a calculation 10 by 10, 5 by 5, 3 by 3, because it's very simple to define. Once your geometry is set, we can come here and just change what's the field size and run the simulation. So let's test this again. Okay, you see, it's although I'm having a trouble. It's still the density is 0. It's not working. So there is something not working with this physics. I hope that this would be fixed. But anyway, let me show you something. This is if you intend to use MMCTP, and this is probably what you're going to be doing eventually, to use MCTP with MLCs or VMAT, IMRT calculations, there are a few things you have to change in the default EGS configuration. Otherwise, you will have a problem with RAM. So let me show you these things. Okay. Okay. So you need to go to the henhouse directory. And you will need to go to the Omega folder. Omega, anything related to Beam and those XYZ, you will find it under Omega. So if I list what's there, you'll find there is Beam NRC and the programs. So let's go to Beam NRC, and then you'll have a long list of stuff. I want to go to the CM, that's the component modules. Okay. These are, so basically, when we, for example, define the linear accelerator with Beam, what do? Very simply, we say, okay, I have a component module slabs, I have a component module dynamic MLC, I have a component modules, and so on and so on and so on. Now, the code for that component modules are actually in this directory. So when you build the linear accelerator, building means it's going to grab the codes into a one big file and then compile it. Okay, so these are, let's say, templates for the codes. You see, these are the slabs should be here. So slabs is here. There is a macro and the component module. It defines the geometry of the component module. It defines some other stuff. Okay, clear? So for variant, for Electra probably maybe you need to look at different component modules. For variant, there is we use the dynamic variant MLC. That's one component module for the true beam, and the other one is the jaws. So this one is, yes, and we have the dynamic jaws. So the dynamic variant MLC, and we have the dynamic jaws. These are the two component modules that are for variant machines. Electra, I think they have two different component modules. So, and I'm going to show you what I'm going to change here. So let's open this file, and this needs to be done once. We're going to open the jaws. So let's open the, which one? Dynamic jaws. Dynamic jaws. Yeah, I want the dynamic jaws. Okay, and we look at the macros file. Okay. Okay. Just after you finish from this, the first part, you will find this is the maximum field dynamic jaws. This thing. I think the default, the value you have is going to be 100. If Bilal, if you go now to your hen house and check what the value, probably is going to be 100. What is this? This is when we do treatments now with variant machines. You have the capability of having dynamic jaws. Dynamic jaws means that as it is going, the jaws are going to move. Okay, they have different settings. So for a full treatment, the different fields or settings of the jaws, if it's usually it's more than 100. So you can have 160, 100. I mean, it's going to be more than 100. So the default value is 100. When you read a plan with dynamic jaw settings, more than 100 different fields, then when you execute, you're going to have a segmentation fault, means that there is something wrong in the memory-wise. So we need to give more RAM. Okay, so here I'm telling it, okay, the maximum field of dynamic jaws is 1000. If I get segmentation fault, then I'm going to increase this number to 2000. Okay, So I try to pick a number that usually fits, all possible, treatments that's going on. So I think 1,000 is a reasonable number. I haven't seen something that requires more than 1,000. Probably it's an overkill. Maybe 500, 200 might be okay, but I'm putting 1,000. Okay, clear? So this is the first thing you will need to change. Because most of the treatments now,
Yeah, it is
dynamic,
showing 100. It is showing 100 here in this.
yes, so the default is 100. Okay, if I give you actually one of my files to run, it's going to give you an error. So if I give you the input file, it's going to give you an error, because in that treatment field, the number of dynamic fields is actually more than 100. Okay, so just to be safe, I went and modified this and I put 1,000. That should be more than enough. Okay, so this is the first thing. The second one is for the MLCs. So dynamic variant MLCs, okay, and macros. And again, if I go down, okay, we are going to face a problem here. So Bilal, check please, what's the default value? It's the 100 or not. This is the maximum number of different fields, dynamic and step and shoot only. So I'll put 1,000. Probably this is the default, I'm not sure. If it's the default, I'm going to change it to maybe 2,000. But for 1,000, I don't have a problem. Things work.
It's 100
So
only here.
100, okay? So we need to change this to put it 1,000. Again, this is basically the number of subfields. If you do an IMRT calculation, you can actually determine the number of subfields. If you play the movie, MLC movies, you will find up to 300, 400 usually. So 100, that's not going to work. So this thing I changed. Okay. A third parameter that I changed is not really important. It's just for my convenience. Okay. So let's go to the, so under hen house, there is a folder called, it's SRC. Okay, and let's look at the files. So it's this EGS macros. EGSnrc macros. I don't know where is it, but probably I'm going just to search for it. So the parameter I'm looking for is called dollar and then chunk, CH, okay, here. Okay. I think if you go and look at the default value, you'll find it 10. This is basically the number of batches. If you're doing parallel processing, your log file is going to be updated, let's say at 10%. I mean, or let me explain this in a different way. Imagine if you're doing parallel processing. You have 1 million particles and you have 10 CPUs. So what's going to happen is first is going to divide the number of particles by the number of CPUs. So that means 100,000 CPUs. Sorry, 100,000 particles. And then it's going to divide that number by this number of chunks. So the default, I think it's 10. This means that,
10, yes.
yeah, so default is 10. This means that 100,000 divided by 10, that is a 10,000. So what's going to happen is that when you launch this simulation, you're launching 10 jobs. Each job is going to take 10,000 particles. Once it finishes the 10,000 particles, then it's going to take another 10,000 particles. So it's the amount of particles that it takes is 10,000 per batch, or per simulation. Now, this means that the log file is going to be incremented every, let's say, 10,000 particles. But imagine if you're doing the simulation, let's say 10 billion or 1 billion, and we keep this as 10, then this is going to be updated every 10 million particles or simulation. So it's a long time. So you don't know if actually the simulation is running or not running. So this is something I like to do. You don't have to do this. It's not required by MMCTP. So all what I do is I change this. Let's
Is
say
it the
100.
same as actually when you do EX, it shows 10 jobs, something like 1, 2, 3, like that, it keeps on going?
Yeah, I think this then is going to show 100.
Okay.
So it's dividing the number of particles, the batches, to 100. I think that's probably So it's up to you, because I like to actually have to see the update, the progress. I am impatient. I want to see the progress going. So if we keep it at 10, okay, then the progress is not going to be. I'm not going to see a change, although the simulation is actually running, but I'm not going to see a change until after a while. So I like to change this to 100. Okay, but it's up to you. Okay, but this is not important. It's not really important at all. Okay, and let's actually, because when I did this, I did not actually compile for those exercises. So I need to change to switch. Let's change those X, Y, Z. So when you do these changes, remember you need to recompile. So I will recompile it with those X, Y, Z. So okay, let's make clean first, and then make. Okay, while it's compiling, this is a plan for a patient that I've imported. The plan has gantry angles and has MUs. You see, the SSDs are not there. It does not detect or calculate stuff from the body. But it's not really important. What's important is where is the icenter. In this case, this is because it's from Eclipse. The icenter is at 0, 0, 0. The center is somewhere here. Maybe there is a way to actually show where the center is, and Andrew can show us, but we will check when he enters. Okay. The first thing you need to do, once you have everything running, or you import the file, the plan, then the first thing you need to do is to calculate. We need to calculate a beam. With beam, we generate phase space file, and then we calculate the dose in the phantom. Let's take another one which I haven't done any calculations to. Let's take this. Okay, so this is a plan. Okay, and it has 9 fields. I did not calculate anything, so I will double click on the first field. I'll get this window, and then I should. What it did is actually it went and opened the template. You see that template that I've inserted there? It opened the template and populated everything from that template. The phase space file, whatever source is defined in that template, it's going to be, you don't need to have it like if you have a clean, if you know, for example, what's the target material and geometry, and you actually want to start the simulation from the source, you can do it, because we can change what the source number and so on. Okay, but in my Linux, the TrueBeam, I have only three component modules: the dynamic JAWS and the dynamic MLC and the slabs, because I'm using a face-based file uh, that is generated above the JAWS. The dynamic JAWS, see, edit, these are default values. All of these values are actually values taken from the template. Now, when I run, this is going to test. So it's running 15,000 histories. So when I hit on run, now we should see here. You see, I'm getting, okay, it uploaded the file and now it's running. It's running on the Raspberry Pi cluster on one single machine, just to test that everything is fine. And then after 1500, we got 124 particles in the face space file. That's the face space file above the patient now. It's not the source. And some statistics that, okay, we can do, for example, number of histories, 28 million. Okay. Remember that value, the desired particle density. If we want 500,000 particles per centimeter square density, of course, this number is rough because we really have just a small number of particles. But I just want to explain this to you. Then the number of histories required to run is roughly this. And if I'm running this on 8 nodes, parallel processing, this is going to finish in about 3.6 hours. Okay. Now I have 50, so I can change this number to 50. Okay. This, I can generate this in 34 minutes, or probably 30 minutes. Personally, I don't do this because I use, in the dose calculation here, I actually, so the default, there is a template also for the dose X, Y, Z. And if you look at the template I have, okay, it's actually a full beam NRC template, treatment head simulation. I can change this to a face-based file. That is fine. Okay, but I like to do it with the template. Okay, so I can save this, and let's do 2,000 particles. Now I'm running a simulation in the patient. Okay, dose X, Y, Z, using the beam library. So if you look here on the left, I'm not using a face space. I'm using a library source. Okay. And the simulation is going to run. Again, at the end, it's going to tell you, okay, if you, based on the uncertainties, let it finish. So basically, it's going to calculate, if I want a 1% uncertainty, probably the number of histories is going to be around 2 million to 3 million particles. And running under 4 cores or 4 jobs, then the total is going to estimate, I think it's going to be 3 or 4. Yeah. So it's about 4.5 million, roughly, okay? Number of jobs, if it's 4, this is going to, so I'm talking about one field only. This is going to take 5.5 hours. That's why I have this huge cluster. So when I do 50, it takes 26 minutes for a single field. Now I have 9 fields. So I need actually, it's going to get the full plan distribution, then it's going to take 3 or 4 or 4 or 5 hours. I could, for example, decide, no, I want to actually run this on 10, and then the other field I'm going to select 10, and you can do it that way. It's up to you. Okay? But this is basically, and what I usually do, I actually put this to 10, 10,000, 10 million. So even 4 million is probably what's required to get roughly around 1% of sensitivity. I do 10 billion, and that's about an hour. So once that is done, then I need to click here, and you'll find now this is going to change that. So now it has created the file, it's uploading it, okay? And if I do SQ, you start to see, okay, my queue is getting filled with jobs. That's why you need to have, I'm wondering, if I ran the same number of particles, let's say on my virtual machine, how long is it going to take? Because that will tell me what's the, equivalence of my 13 Raspberry Pis to the 8 cores on my CPU, my laptop, because the cores are faster on my laptop than the Raspberry Pis, but that is interesting. And of course, if you have a dedicated machine, 24 cores and so on, this is going to be fast. You don't need to have 5 of them, probably. But you're going to test how, the computational power. You're going to test that. Okay, so now 13 is the last, my last Raspberry Pi, and it's going to be, it's good. See, it takes about a minute just to submit the jobs. But they're running, and yeah, they takes time. So here, so this is now, you see now the progress is shown. If we did not change that value, from the n chunk to, let's say, 100, you're not going to see this 1.4, 1.7. You're going to see probably larger values. It's not going to update as frequent, because what happens, this reads, uh, it reads the log file. Okay. Yeah, this is the log file. This is an old one. I think I need to delete it. But this is the log file. So if I do more again, okay, you see this now gets updated more frequent when I change the n chunk to 100. So what happens is MMCTP is going to open this log file. It knows it needs to do 10,000, 10 million particles. This is the number of particles that have been processed here on the left. On the right is the number of particles remaining, needs to be processed. But now it has, for example, results for 360,000 particles. Okay, and the 50 is the number of cores it's running. So now I submitted on 5, on 50, then. So let me delete this one. So I'm going to let it run. So I need to repeat this for each field. So now we need to go back. I need to at least, even though I'm using libraries, I need to at least run the beam once. So I run it. I don't click on the calculate beam. I don't want the phase space file, so I will never click on this. So if I wanted to, for example, let's go and try to calculate the second beam. If I try to do this, I'm going to get an error. I believe there is going to be an error. So let's see. Oh, okay, it ran actually. So there is no error there. That's fine. I thought there was going to be an error because an input file for the beam was not generated, but it seems it will automatically generate the input file, and that is fine. Okay. So this is what happens then at the end is here I've done a head and neck. Okay, let's see this case here. When a shell is running, it does not allow you to actually select anything else. So let's see what's configuration. Let's kill all shell tasks. Okay. Okay. This is a, let's try another, let's see if it's going to actually, this is a head and neck case. And I just wanted now to download because this was the last field. I did this last field. I was doing this calculation today. And I was just waiting for the last field. Now it's done. So once all the beams have been calculated, then it's, so these are the beams. See on the list here. This is the eclipse plan. Let's get the structure, those, so it's a head and neck. I don't know which structure was that because I have done a lot of structures here. Is this PTB? Yes, so this target, this is a PT, this is actually head and neck target. And these are the parotid. One thing also I face difficulties, I cannot scroll. I need to scroll soup if I cannot, but at least these are the parotids, they're shown here. These are for this structure. So this is the eclipse, this dose distribution. Okay, that is the dose distribution from eclipse. One problem I'm facing is to generate DVHs for this, but with MMCTP, once all the beams, so this is the field, this is the dose from the field. From this field, you know, you get the dose from each individual field. Okay. And then when all fields are calculated, this is now the total of all the fields. Distribution looks very good. It's you know, it's very close to the original. The only problem I'm facing is for the Monte Carlo, I need to define, remember the output or monitor unit with Monte Carlo. So how many particles or what's the dose per particle equivalent to 1 centigrade per monitor unit. That I don't have that configured. This ideally one would generate this physics phantom, do the calculation very, you know, with a lot of particles, and then get the dose at Dmax. The dose at Dmax, I think here it requires it in gray. So the dose in Dmax, and our beams, for example, are calibrated 1 centigrade per MU at Dmax. So we need to do the conversion, and then we can use that value to calculate monitor units. Now for DVHs, here we can normalize. You know, at least we can look at relative stuff. So although it's not going to give me any information because I cannot do DVHs now. But we can normalize actually. We can extract um, profiles. This would be nice when you do the commissioning. Imagine if we manage to get that physics patient running, then we can just use the ruler and so this is the ruler, and we can somehow extract, let's say, a profile. We define what is the initial and final point, and then we will hit on calculate. So this is the plan. I'm not interested in the household units, but I'm interested in the plan. And when I hit on show, then we get, let's normalize this. Oh yeah, I see what's the problem because this is outside. Okay, so here, and we put this. Okay, so this is the first point. I'm gonna take a profile like this. Yeah, because I was selected the top. If I wanted this part, then I should select, I think this is right. Yeah, calculate, and then we select here and show. Yeah, this is the profile. But of course, the doses are in, per particle, those the small values. We can normalize it to maximum and compare to, so let's normalize it, and it's the maximum. Okay, the maximum here. Well, let's normalize it to a point. So minus 1.03, so that is minus 1. That's not, well, let's put that minus 1. That's 0. What is 0? 0. So minus 1. So I'm going to normalize it to 6.288. 288 e to the power minus 10. Okay, so now roughly it should, yeah, this is normalized. And what we can do, keeping everything the same, I can select from Eclipse, and let's calculate, and then we can show from Eclipse. So this is the profile that package Monte Carlo, and this is from Eclipse, and we can show that. And what I need to do is for Eclipse to normalize it. So we normalize it at minus, roughly here, so 0.9813. So let's try that. And okay, there is something wrong in my normalization, I think. Uh, it's normalizing both curves to same value, it seems. This is not normalized. This is, I don't want this. Okay, let's look at this now. I select this point or this point here. So normalize 6.6 e minus 12. So that's the curve. And then let's do the other one. Show it. And let's not, okay, let's move this. Okay, here. This is, so roughly 2.25. 2.25. Okay, so this is the difference between the Monte Carlo and this the Eclipse and this Monte Carlo. I don't know why uh, the profiles are not matching 100%. There might be some geometry problems that I need to look into more. But at least I get the shape, the proper shape. Yeah, this could one thing. This could be it's the leaf gap. Maybe it could cause this problem because it seems that there is more transmission. Of, I'm not sure why they're not. Love the class set. Okay, okay. Yeah, apparently yes, it's recorded. Yeah. So anyway, this is the part that how to run and the also DVHs. That's something that does not work yet for me at least. I was hoping Andrew to join us, but he seems to have he's on call. And let's see if we can get the PTV. Which one is so when I click on show updating control points for DVH calculations, he told me to wait, so I should wait. And let's see if we're gonna get something. Oh yeah, it's calculating it. Okay, PTV not ready for device calculation, creating structure points. Okay. I've tried it, it does not work on my machine, so we're gonna wait, but I don't think it's gonna work. Okay, so I hope this was, useful. And definitely, you can tell now, the simulations are gonna take time. They're not gonna be done in like 10 minutes or so. This is, remember, EGS is what's defined as an accurate Monte Carlo code. And even with waiting, like in my cluster, I still need to get to wait 30 minutes just to get an uncertainty down to 1%. There are commercial uh, codes that they implement some sort of ways to speed up or get clinically acceptable results in a shorter time. So, for example, one way of doing this is you instead of simulating the particles, maybe you can just generate kernels with with Monte Carlo and then use that to actually calculate those in a phantom. It's going to be very, very fast. And clinically, you don't want something. I mean, if you get an uncertainty up to 2%, that is still fine clinically, I believe. Other ways is, for example, so suppose we track a history. Okay, so I assume now, but the when I define when I say history, it's known to everyone. So we have the history of particle. We know deposit where it deposit doses. Imagine we can just duplicate, not duplicate. I mean, repeat that exactly history or the doses that it has deposited in let's say 100 different locations, or we make 100 different tracks. So this should make the calculation, faster. These are called fast calculation techniques. Clinically, they're acceptable, but EGS, remember, it's an accurate. It's more accurate than others. So the
Definitely, Andrew is
simulations are
fine.
going to take a bit of time. So Andrew has joined us. Okay, hello, Andrew. Andrew. Okay, we'll give him a minute. So my suggestion, get a computer, put it in your clinic, run the so if a simulation takes 2 days, it's still not going to do it on your laptop. That's going to be fine.
Can you hear me, Wamid?
Yeah, go ahead.
Okay, I think people can hear me now. So I was waiting Wamid to join in, and I didn't realize that I could just reuse the password from last week. So I'm here now. So what I wanted to show everyone was the DVH calculator, because Wamid was expressing some concern as to it wasn't calculated on his computer. I just want to go over how it works.
You can share your screen, Andrew, by the way.
Okay, I'll share my screen and we'll just do a little bit of a review on that.
By the way, this is still doing a DVH calculation and it's not working.
Yeah.
So I'm going to leave it while we share your screen. Okay.
So I think, Wamid, you have to stop sharing your screen before I'm allowed to share my screen. So here, I hope everyone can see, this is a head and neck calculation. It's zoomed in, so I'm going to take off the dose grid. This is the PTV volume. And there's other structures in here. The structure list is in this right corner. We'll just focus on PTV volume 1. This is an IMRT plan, so there are a number of fields, and there's a number of dose calculations that are pre-calculated. For the purpose of demonstration, I will just focus on this one dose distribution. It's in plan, it's in course 1, it's beam 8. So this is what I have selected. When I click on the dose, you can see that there is dose there. One thing that you can do that you may not be aware of is you can set your minimum and maximum. So this is a dose that goes up to 74 gray. So if I just want to look at the 30 gray to 75, that cleans up the view a little bit, because you'll have dose in air by default as it's part of the calculation in dose XYZ. So this is one way of cleaning the view up a little bit.
Andrew, EGS
Yes.
has a feature of zeroing the doses to air.
Oh, okay. I wonder if I've included that in dose XYZ.
Yeah, I will look into it and then I will let you know about that, because I think you can clean the problem is then if you have air inside your patient, that's the problem.
That is a problem, yeah.
But probably you don't want actually doses to be recorded there. It's not of interest.
Yeah, I can see what you're saying. Yeah.
Yeah. Okay.
So this DVH, there's a DVH calculated for each dose distribution, and it has this big long list that you scroll through. It's maybe not the most elegant way of displaying them, but if I delete this PTV1 for this dose distribution, you can see that MMCTP will quickly, and this is what it should do, recalculate that one. So now it's back. And we can view it. And this is the DVH for that single beam over the PTV. So I'm not sure, Wamid, why your system isn't working like this, and we could look at that together maybe offline. But I just want to go over how the DVH is calculated at this point. So I started showing you guys the dose grid, and this might be very difficult to view on people's screens. What I'm trying to illustrate here is the cross points here are the center of the dose grid for the dose distribution. So if this point lands within this red line, that's considered a point inside the DVH, and it's going to be calculated. So now we're going to go through the DVH calculator. So I'll share a different screen. So the first thing that you have to consider is how these structure points are imported into MMCTP. And that comes through DICOM files. And they get converted into a XYZ position for a contour point in centimeters. And then MMCTP will write a list of those points per slice as a text file. And this is called the RT structure file. And you can open up these files and review them for yourselves. So they're not labeled as a structure name. There's structures 001 to however many structures you have. Within the structure 005 for this patient, that was the PTV1 dataset for contours. And there's some identifiers here that come through from DICOM, and the color and the number of scans represents the number of CT slices. So for each slice, there's a row and line entry. So you have, again, the number of slices, 233, and then it starts going from slice 1 all the way up to the end. So slice 1 starts at Z position of 7.4, and there's 0 segments in slice 1. Over here is where you start to see some contour points for that volume of PTV1. And we have one segment. That segment has 53 points, and then it starts listing the points, and these are in centimeters. And the last point is the slice position. So the slice position is consistent across that slice, and these are the X and Y positions of each point. So you start from this data set, and now you have to create points within this volume, because these are just the points that define the edge of the volume. So there's a number of ways of doing this, but I'm just going to show you how MMCTP is currently coded. So we go from these DICOM coordinates, which is the contour edge, and we convert it to a polygon class within MMCTP. And a polygon class is a class that was written in Zojo by another user that I've incorporated into this program. So it likes to use integer values. So this class, we have to convert the centimeters for the external points into integers. So that's what these two lines are doing. It's taking the centimeter point and giving it an integer value based on a starting position of a 512 by 512 image. So then you have to round this. So we're rounding down by using this floor routine. And then we add the integer points into the polygon. And the reason why we're using lists of integers is because it becomes easier to paint these polygons onto a graphics. And that might be a little bit hard to explain in words, but I'll show you the code afterwards, and maybe it makes more sense then. So now we have an array of integers that define the edge of the contour. And we need to make this an array of points so that we not only include the points on the edge of the contour, but we include all the points within the contour. And once you've accomplished that task, you then have the full volume of points inside a contour at a consistent resolution. So that is done using these two arrays, or these two methods within MMCTP, the make array of points, and then you can either make array of points from images, or there's other methods of making these array of points. And I'm just going to show you the images for now, how we do that in a second. But first, once we have this array of integer points, you can then convert that back into centimeters in X, Y, and Z. And that's where we actually start to calculate a DVH. So there's a routine called calculate DVH HR. And that is going to go through this list of array of integers, convert it back into centimeters. So you have the centimeters in X, Y, and Z. And then this is the routine that interpolates a dose value at that specific point. So RTOG dose interpolate is used throughout MMCTP for all different applications, but it's used heavily in the DVH calculator. So the higher the resolution, the higher the number of integers you'll have to define that structure, and the longer it's going to take to calculate all of those interpolations, because this is an interpolation. It's interpolating in all directions. So between the slices, between points in X, Y, and Z. Okay, so now if we look at
Andrew,
yeah.
Now, conventional trigger bank systems, do they calculate DVHs the same way, or each company has their own way of doing this, and that's why you made your own code so that you make it consistent on MMCTP?
Well, I think every company like Pinnacle or Accuray or Eclipse, they'll all have different methods on how to do that calculation. And the method that I'm displaying might be the absolute slowest method of doing it, because it's not using any, it's not using a mesh, which I believe most companies try and create a mesh which can have various degrees of resolution to try and speed up the calculation. This method, no matter what the size of the object, it's going to have the same spacing between each calculation point to get dose values. But that said, I haven't looked at how other companies do this calculation.
The problem I see, for example, is if different companies have different ways of calculating DVHs, then if you want to compare, let's say, a plan from Eclipse compared to MMCTP, then one has to be consistent, has to recalculate DVHs in a consistent way. So I agree probably we cannot import the DVH from Eclipse and compare them to what is calculated with MMCTP. Probably
Right.
there's going to be a small changes, and especially when the volumes are small, probably that's where we're going to have a big discrepancy.
Yes. And I've noticed that, Wamid, I've noticed that quite a bit. So you'll see if you have a volume in Eclipse, you import it into MMCTP and you recalculate, there's going to be a different volume. And within MMCTP, there's actually two ways of calculating the volume. The DVH is only calculated on one of those methods, which is the method I've just shown you. But the other way of calculating a volume is to look at those contours, the edge of the contour, and calculate an area per slice, and then sum that up. And so that's one method of using a geometric calculation of volume. And then the DVH calculation that I've just described, you'll be summing up all of those integer points within the structure and assigning a delta volume to each integer, and you multiply it by the number of integers, and that's your structure volume. So even within MMCTP, there's two methods of calculating a volume, and they're both displayed, so you can get an idea of discrepancies. It's not to say that one is better than the other, but when you do see discrepancies, it should be an indication that maybe it needs to be investigated further to figure out why the volumes aren't closer.
Andrew, there, we have a question from Singh. Oh, go ahead, Singh.
Andrew, what is your recommendation for deciding the resolution for a structure? Like, let's say for those calculation metrics, it could be like 2.5 mm or 3 mm grid spacing. But for DVH calculation, it may be different. So,
Right.
yeah. So what is your recommendation regarding DVH recalculation?
My recommendation is to leave it at the resolution of the CT scan, and that's the default resolution. Now, if you're using this calculation for a very large volume, maybe you should consider increasing that to increase the efficiency of the calculation. And then the opposite would be true. If you're using these calculations for very small volumes, it's possible that the CT resolution is not small enough to capture what you're trying to evaluate, and you'll need to decrease that. So there's no solution to that question without knowing exactly what your end objectives are. But the default calculation is the resolution of either the CT scan or the dose grid. And those are kind of first approximations. Like it's a good starting point, and then you can evaluate if you need to make changes. So where I wanted to go.
Yeah, as in commercial TPS like Eclipse or Monaco, when we change the dose grid spacing for DVH, like bin size, dose bin size, that will also affect the DVH doses.
Yeah, that's true. So
So
the
how
way
can actually calculate the close to the real values, that what the actual dose is going to particular structure? If we change the dose bin size like from 1 CGY to 10 CGY, then its value definitely going to change.
Yeah, that's a good point. Yeah.
So,
So
how can we then correlate that this much of dose bin spacing should be used for while calculating DVH?
well, I don't have a good answer. I mean, I think it's user dependent, and I think you
And
just have.
I think also that, I mean, the CT image has a specific resolution. So it does not make sense that you try to calculate a DVH with a resolution smaller than the CT image, because then it's going to interpolate things. I don't know if that value then is going to be closer to the true value or not. So I tend to agree with Andrew that, okay, if the best possible thing you could do is to calculate your DVH with the same resolution for your CT images. Now that might take a long time to calculate. It also depends on what you're looking for, how accurate you want to you know, like in a clinical situation, maybe that's not really important to calculate deviations for a long time. You'll be happy with the higher uncertainties on this, or maybe not. So it depends on what your goal is. But I tend to agree with CT resolution. That should be probably the limiting factor.
Yeah, and the reason why I say you can go smaller than that is it really depends on your application. And for our application, we're looking at microbeam radiation therapy. So our dose calculation is actually finer than our CT resolution. And it's kind of a unique situation, but the only way to see that level of detail is to look at smaller voxels. So it really depends on the application, because we can't get micro slices using our CT scanner in the clinic.
But the DVH at the end is also controlled by the structure. It's not, we can always with Monte Carlo make the dose resolution as small as possible because we control these voxels.
Yes.
Yeah. You know, not a problem. But the problem is the image. The CT image comes at a given resolution. Now we want to calculate at a smaller level. So we have to accept, that there is going to be interpolation.
Right.
We have to accept whatever errors are generated. That's all.
Right. So I was mentioning using the images to calculate the DVH points, and I just want to show you how that's done. So that's the quickest method of generating this list of integer points, is to use the graphics routine. So this is just an overview of how that works. You have your polygon list of integers that define the outside edge. You then create a picture at 32-bit resolution and 512 by 512. And you fill that picture with these polygon points. So that's this routine right here. So now the entire volume, it would be an area per slice, but the entire area of that contour gets filled in with a very specific color. And once you've done that, you then go down here and you count the number of pixels within that image that have that color. So this is where differences in how graphics routines are utilized between Mac, Windows, and Linux can result in edge effects of that contour being slightly bigger or smaller, depending on if this fill polygon includes a certain voxel on the edge or not. So that's just a quick overview of how the list of integer values are created that define the full volume of your structure. And with Windows machines, what I found is this doesn't work very well. It works really well with a Mac. So with Windows machines, we actually have to use a second method to verify that each pixel is actually within that contour and not outside of it. So that's what this within function does. So now we're still creating a list, but we're using other routines to determine if this pixel is within. That's what this method does. If this pixel is actually within the edge of the contour or not. And you can go through these routines and see if they're making sense to you. But this is to paint the structure points for Windows. Yeah. So that's
you do this with pictures because it's faster with the GPU, these calculations.
Yeah. So I hope everyone's seeing the MMCTP now again. I just want to make sure I'm sharing the right screen.
Which version of MMCTP of Zojo, by the way, do you have?
Oh, let me just open that up. So I'm using version 2019 release 3.1.
That's two versions. So I think there is an update 3.2,
Okay.
and they have released the 2020 version. Okay. A few things that I see on my version different than yours is, for example, when you point your mouse into the images, you actually get a dose value recorded. I don't get that. It's not there.
That's interesting how there's so many differences between the different platforms.
Yeah, and so I don't know why. Either I'm using a older MCTV version, but I believe that's some fundamental things you took care of. I'm sure about that.
Yeah, it should be working appropriately. So going back to your DVH options, use the CT grid is the default one selected, or you can choose to use the dose distribution grid should you want to change that. And then this last option is really only for very specific cases where you need to change this value to a very specific number for your needs. But I would just leave it at the CT grid. And if we look back at this DVH, you'll see some statistics here. So we have the total volume of this structure using the integers. So counting all of those integer values at a very specific size per pixel to get us a voxel size, this gives us one geometric volume. And then you can see calculating the volume of this structure based on the coordinates from DICOM and calculating an area per slice and then adding those areas up for all slices, it'll give you a different geometric volume. So where is the truth? Well, it's somewhere in between, probably. And this is where you would compare to Eclipse as well. And Eclipse might match this one, or it might be closer to this one, depending on the details of that volume and how complicated the structure really is. So sometimes these volumes are a lot closer in correlation to each other. Like if we look at, let's look at the chord. So here there's the volume from the integers, and the volume, the geometric volume, is a little bit closer, but there's still a difference. And I don't have an Eclipse calculated one to show anybody right now. Yeah. So I think there's improvements to be made on how DVH are calculated within MMCTP to overcome issues such as this volume discrepancy and the speed of the calculation. But if anybody's interested in exploring with that, they can contact me and I can help as much as I can. So I think that was the only thing I wanted to present today, Wamid. I don't know if there's specific questions on details of the code. I can dive deeper into those questions next week and continue to offer my insight on how the code was developed and why it behaves as it behaves. And Wamid, one thing I noticed, you were trying to switch plans while something was calculating.
Yeah.
And you couldn't switch to the other plan. And the reason being is the shell that communicates between your cluster and to MMCTP.
It's busy. That's some, yeah, I know that. And you can always kill and then, switch. It's not a problem.
Okay, good.
Yeah. But the things that, there are a few things that I have a problem with. Just wanted to show you.
Okay.
They're not going to be fixed now, but this is what I've noticed is you actually now this is those, and what about here? Somehow when Andrew shows up, now I see the value of the dose. Okay, I wasn't seeing this, but now I see it.
Nice.
So this is because I wasn't getting this value. Okay,
Yes.
I was getting the coordinates, but not the value. So now this is fine. But again, see the DVH, it's not no calculation. That's something probably I need to explore.
That might be something to do with the new upgrades to Zojo.
Yeah.
It's interfered with how the calculations are being run. So I can help you out with that, and we can try and figure out what's going on.
Yeah, sure. There are a few things that I have, with Catalina, the compiled version does not work on Catalina immediately.
Okay.
So I have actually fixed something in the code that probably I can share it with your kit, so you can implement it in the newer version.
Okay.
When you compile. Okay, guys. So any other questions for Andrew.
Yeah,
Is it,
I have a few questions from
okay, go
Andrew.
ahead. Yeah.
Andrew, as we all know that there are three grids. Like one is belongs to the city image dataset, another one is belong to the DOS grid, and third one is the belongs to the DVH grid. Like for the city images, we have a just fixed resolution. Like we cannot play with the city image resolution. Like for those metrics, we can play with the DOS grid spacing. Similar manner, we can play with the DOS volume histogram matrices, which we reconstruct from the DOS grid. So, like in Eclipse or Monaco, what I have observed is when we export the DVH with the 1 CGY resolution or dose bin setting, then uh, the doses which are shown in the Eclipse TPS or Monaco TPS is very near to the 1 CG, very near with the 1 CGY dose grid setting. When we export the same like at 10 CGY dose bin setting, then these values are too much deviated from the TPS values. So I would like to ask that what is the effect of this dose bin setting on the dosimetric calculation of different structures?
I think you're asking for the bin setting. Is that it? Or the
Yes, bin size for DVH. Yes.
So the bin size, I can show you how it works. It's interesting. I think it's a little bit different than how the bin size works in the commercial treatment planning systems, because the way I'm binning the information is really after the fact. So the total number of voxels is decided before the binning, and binning is just the creation of the histogram for MMCTP. So you can see that, I don't know if you can see this here, but all of the dose points are
Share
created.
your screen, Andrew. Share your screen.
So here we're calculating, this loop is calculating all of the dose points for the total number of integer points that we're going to calculate over the volume. And it's adding them to an array. This, yeah. So you get an array of points that include every single element of that DVH. And then from there, now we start to calculate a histogram. So we're looping over all of these dose values. And this is where the binning occurs. So you can change the bin. It's default to 100 bins. But you can change that bin setting. Now, how a commercial system uses the word bin and a bin setting is very different than I think how I'm doing it here, because I'm just using it at the histogram point. Does that, I don't know if that answers your question, because you're asking about how commercial systems work with bins.
Okay. So you are actually splitting the dose matrix into 200 bins by default.
It's 100 bins, or is it?
Okay.
No, let me just, so when we look at a DVH, I don't, oh, right, sorry. It was right here. So you have this DVH bins. So there's actually only 50 bins. for these calculations, but the user can enter 100 here or 200. And all this is going to do is give you more resolution in your histogram, but not more resolution in the calculation. Like the calculation is based on the geometrical points and their distance between each other.
Is it necessary to recalculate again and again if we change the bin size of the DVH?
Well, it is just because of the way I've calculated or created the code, because this routine that calculates the DVHs contains both the calculation of all the doses at each point and then the binning of those doses. So right here, this could be a separate routine where if you change the bins, you're going to change how the DVH is displayed.
Okay.
Yeah, I hope that answers the question.
Yeah.
How many people are working actually on Zojo, development of Zojo currently?
Are you asking about Zojo in general? Like how many, what's the...
No, on MMCTP, sorry. On MMCTP, yeah.
I think there's a handful of people. There's not a lot of people working on it. Every now and then I receive an email asking for help with installing. So I think there's a barrier to install, and then people come across issues and the documentation is not there to walk them through these issues. So there's not a fair number of people that are working on it.
This is why when you have these videos on YouTube, interested people think they can.
I think it's a great idea, Wamid. I'm glad you initiated it.
Listen to this, look at the steps they contact. A lot of people, I got the positive feedback just on the EGS part, installing EGS. A lot of people were struggling to follow the instructions, but when we showed them on a video, then everyone got it. 99% of people got it right the first time. So I was happy. So that's why when you're having these recordings online, I think, and I hope with MMCTP, this is a way to actually promote it, to get more people using it, and develop, you will get suggestions from people, new ideas and so on. Zojo is not a common programming language. Not a lot of people know how to program with Zojo, but interested people will probably start to learn a bit of how the code works with Zojo and so on.
Exactly. Yeah. Well, I'm glad I could offer.
Well, I'm very happy you joined us. Everyone here is grateful to these sessions, and we hope next week we will have more questions. Definitely, I will try to work on, show you some of the problems with the code and probably some of the fixes that I came about, and you can help me. Others could also, have their share of questions next week.
Yeah.
Okay. Okay, Andrew. So. Thank you very much for being with us, and thank you all. So I will. It takes time to have the recording on YouTube. So by tomorrow, probably it will be there, so people who can watch again.
I was watching it as we were going, Wamid.
Yeah, but when it's done, it takes time. Okay, then it will be available.
Okay.
Okay. Thank you very much for all, and good night. Thank you, Andrew. And good afternoon, Andrew, for you. By the way, where are you working now, Andrew?
I'm in Saskatchewan.
Okay, with Kristen Stewart?
Yes. Yeah.
Okay. Good.
And Varun is here as well, actually.
Who?
Varun? I don't know if you...
Yeah. I met him actually at 2 years, last year in Vancouver, actually.
Yeah.
He was there at Comp.
Yeah, so we have quite the McGill collection now here.
Yes. Yeah. Okay then, everyone. Good night, and see you then next week.
Yeah.
Bye-bye.